What's dice we talk about the cosmological perturbations, especially focuses on the by using the Newtonian gravity. This is Newtonian gravity regimes can only apply to the only for the small scale and the non-relativistic case. Such a cosmological perturbations correspond to the inhomogeneous universe case. In the standard cosmology, generally we consider homogeneous universe. Like as homogeneous and isotropic assumptions, they give the apparent W matrix, and we solve the Einstein's field equations of the general relative theory, and we obtain the lambda CDM model and such thing. But under such an inhomogeneous universe, there will be some density perturbations quantity, and it will grow. So the such density perturbations satisfied some equation of motion, and we can bounce the solutions for each type, and this gives a structure formations for the large scale structure. So first of all, we will focus on the Newtonian gravity case. There are three quantities, which is the appears in the fluid dynamics. The first one is energy density, correspond to the mass, and the pressure P, and the velocity vector U. This satisfies the two equations. The first one is the continuity equation, correspond to the energy conservation, and Euler equation, which correspond to the momentum conservation. So the continuity equations, there will be the energy density and the energy flow as a multiplications of the law and the velocity. So this gives the energy conservations, this time derivatives and the partial derivative. Similarly, for the Euler equations, there will be the possible the convex time derivatives here in terms of the velocity, and this is a form of the Newton's second law of the force, F equals ma. So this gives F the gradients of the projects gives the force and the as the per unit volume, and also the gravitational potential is capital pi. The gradients of the capital pi is the gives the force, and that is also the gravitational potential satisfy the Poisson equation. So based on the such two equations, we will find evolutions of the small perturbation. So the energy density can be decomposed in the homogeneous background, low bar, plus the small perturbation, delta low. Similarly, for the projects, P can be decomposed into homogeneous part and the perturbation part, also for the velocity and also for the gravitational potential. There are some several cases. First of all, let's assume that the static space. In the static space, and also we assume that there is no gravity, so gravitational potential equal to 0, and all the quantities of the homogeneous background parts, low bar, P bar is constant, and the velocity U bar is also the 0. Then the equation of motions are given by such a form. So we will only consider the linear term. So there will be the delta low as the density perturbation part from the continuity equations, and because the low bar is a constant, so only these terms are remain, and for the spatial part, there will be the low u in here, but the u bars are equal to the 0 vector, so only the vector u's remain, and for the case of the low, because the vector u is already first order, so the homogeneous part, the low bars remain. And for the Euler equation part, similarly, only the low bar and the vector u's remain for the time derivatives case. And that because the delta low, times the u bars are equal to 0 because the u bars are same with the 0 lattice. And for the right hand side, the gravitational potential equal to the 0. And also this laws are, comes from the 1 over the law in the right hand side. And the partial derivatives as gradients of the process. We consider the first order, so the delta p is the result here. So if we ask the time derivatives for the first equation and the partial derivatives for the second equation, then the right hand side some terms the vanishes. So the for instance, the right hand side of the first equations and the left hand side of the second equations cancelled out each other. So the only remaining term is the second time derivatives of the energy density perturbations and the second partial derivatives of the process density perturbation. And if we define the process perturbation or process fluctuation, delta p, as the proportional to the density perturbation, and the coefficients are given by the speed of the sound and the speed of sound cs, then we can obtain the equations for the density perturbation delta low, which is satisfied by the wave equation form. So this is equation for the equation of the motion for the delta low, and the solutions are given by the plane waveform with exponentials vector. So the omegas and the wave number k satisfy the following differential relations with the speed of the sound. So the density perturbations that just propagates this over the space-time for the static case without the gravity. So now let's insert the gravity, then it makes this additional term in the right-hand side with the gravitational potential. The first equations are given like this. There's a first linear order. So the left-hand side is given by the gravitational potential that apply. And second, in the right-hand side, this is given by the density fluctuation, delta low. So the because the originally the only equations of form has one over the low gradient process and the gradient gravitational potential. So this gives additional terms low bar in here, and the delta low so coming from the gravitational potential because we act the partial derivatives in the Euler's equation. So this gives the Poisson equation. So automatically this gives this right hand side. So if we move this term to the left hand side, then with the wave frequency omegas is given by the two terms. First of all, the speed of sound, which is the contribution from the process, and the second one is the contribution from the gravity. So there will be some critical wave number which makes the omegas becomes the equal to the 0. Let's call that as the Jeans wave number Kz. That's given by the this quantity. So if the k is larger than that critical number, so the wave length is smaller than this length, lambda j, defines as the 2 parts of the wave number, then the fluctuation satisfies the some of the positive frequency, so it gives the plane wave solution. So the density perturbations that oscillated. This case is when the first terms, the speed of sound, the process contributions are dominant. So the process contribution dominance mean that there will be some repulsive force, so that this gives oscillations. But when the the scale of the length is larger than the Zin's length, so the wave numbers are smaller than the Zin's wave number, then this gives the imaginary, the negatives of omega scale, so the imaginary frequency. So the solutions are given by the exponentially close to the decay form. This is case of the gravity dominant case. So the forces that act by the attractively. So there are two different regimes. Depending on the length scale is rather than the distance length or not. So now let's turn to the next cases. Actually, the universe are expanded, so that we can insert the effects of the expanding universe. There is some scale factors, which gives a relation between the physical distance and the moving distance. And if we ask the time derivatives on the physical distance, then it gives the velocity u. And the time derivative of the scale factors gives the Hubble's parameters, and the time derivative of the moving distance gives the moving velocity v. So there are the two different coordinate regime here. So first is the physical distance r and the moving distance x. So the time derivatives is also different for the prime sort r and the prime sort x. So that there will be additional term. So there's a relation between the partial t in the r and the x prime by using the chain rule. And by using the scale factors, that this is again by the Hubble parameter form. So under the such expanding universe, the equations of the motion for the conservations are different. But sort of the continuity equations, originally the time derivative is given by this in the r prime, but it will change it in the x prime by using the moving distance. So this makes a different. This gives additional terms that which is includes the expanding universe in terms of the Hubble parameters here. And here's the delta is again by the delta low over the low bar as the density perturbations quantity. So that was one. The continuity equation. The left-hand side is the time derivative of the density perturbation, and the right-hand side is the partial derivatives of the density perturbations. So this is correspond to the u, factor u, already we found here, and this one is low. And this is partial derivative thing, and there will be some scale factor here, because here's the partial derivatives r that changes to the derivatives of the x. So if we consider some zeroth order, the homogeneous part low bar, then it satisfies the continuity equation, and the low bar is proportional to the h to the minus 3, which is the common result for the Baptist dominance composition. For the first order, we can obtain the equation of motions for the first order density perturbation. First of all, yes, here we can extract the low bar and the deltas here, the left-hand side and the right-hand side. We can obtain the low bar and the HAX as the first order, or the low bar deltas HAX, and also V the first order. So the low bar 1 and the V. So there are two terms here, and some terms cancels out each other, and the time derivatives gives a two term, and some terms are equal to the zero, so because of the static assumptions, and so the remaining terms are only three things, and so this is correspond to the delta dot, time derivative of the delta dot. the time derivative of density perturbations are given like this, and the second terms are still remain. And for the third terms, okay, yeah, so these equations correspond to the not static behavior. These equations correspond to the zero to the terms of this equal to 0, and these two terms are cancelled out because a different sign. Similarly, so we cancel of signed all equations with the expanding universe, and the results are following. So the left-hand side, this is correspond to the accelerations with the expanding universe effect, and the right-hand side, there are the scale factors from the A, which is coming from the special derivatives from the r prime to the x prime, and the first order equation delta p and delta phi, and for the two equations that are similar, so we can ask the time value derivative and spatial derivatives each other, and sometimes I cancel it out, and this gives the equation of the motions of the density perturbation. So here is the result. So there will be the two time two time derivatives delta dot, and the sum of the friction terms with the expanding universe effects, and also the scale factor sum. So these two terms are different terms. Other terms are presence contributions and rapid contributions are same. So similarly, so we can obtain the Jeans length and some Jeans width number, and there will be some of the friction term effects. So the sometimes the damped over the cosmic time. Similarly, still when the length scale is larger than the Jeans length, and it gives a closure of the density perturbation. But if the length scale is still smaller than the Jeans length, this gives a damped oscillations. This means the Jeans instability. So now, so we will apply such equations to the some matter fluctuations, especially the document case. So there will be we will apply the matter fluctuation, and there will be some of the several errors in the universe history of the universe. The first one is the matter dominant. In the meta-dominant case, the process is equal to the Jews, and there are no speed of the sound, CS equal to the Jew. And in this case, the scale factors is proportional to the T to 3 over 2, and we can obtain the Hubble parameters. This is a result of the Boltzmann equations. And if we insert these ones for the first equation, so the Boltzmann equation, this is correspond to the A dot over the A square here. And there's only matter contribution to the analysis. So this is the given like that. By using that, we can calculate the equation of motion for the density perturbations that M. So I insert this Hubble friction term here. And the second of all, okay, so the CS is equal to 0, so the third terms disappear, and the right-hand side, the gravitational potential term, such gravitational contributions, the can be changes by the Hubble friction terms, and Hubble friction terms can be changes in the time function of the time. So the remaining three equations the following. So if we solve this equation of motion, there are two modes possible because there is a second difference equation of motion. So the matter fluctuations are proportional to the t to the -1 and the t to the 2 over 3 as the two modes, and the second equation is proportional to the density matter density perturbations that proportional to the A. So this is correspond to the glowing mode. And for the radiations dominance case, still okay, so there is some solutions in the radiation dominant case, so we can install the Hubble relations here, and also there are some gravity contributions and some densities components coming from the radiations part and the matter part. And still the projects, also the projects given by the one over the third law, so the speeds of the sounds also changes can be changes here, and because the matter components it can be ignored, so the this term can be negligibly small because it is a radiation dominant case. So this can be still proven by here. So the two time derivatives of the delta m is given by the delta m of the Hubble unit time, inverse of the Hubble unit time, and the h is minus 2 given by this term with the burst Bridgman equation. And because of this is the radiation dominant part, so this low bar r is extremely greater than the low bar m. And so this term is negatively small compared to the burst term. And under such equational motion, the possible solutions as the density perturbation is a constant through all the logarithms. So during the radiation dominance, the matter past is very slowly grows. And finally, there is dark energy dominant. In this case, the Hubble's term is very constant, and the project again by the minus of the energy density. And similarly, the binary terms, the gravity condition contribution is extremely small. So the equation motions again such a form, and the possible solutions there are two most constant forms, and the other one is a to the minus 2. So the delta m's methods fluctuations stop growth in the dark energy dominant era. So now here is some of the answer of the today's story. We consider cosmological perturbations related to Newtonian gravity, and we applied the methods fluctuation case. And in the next video, I will discuss about the cosmological perturbations by using the general relativity theory, so like the perturbed matrix and the perturbed matrix.